Okay, we should be live, just testing my sound and everything. Start developing in a second. There's a lot of interesting things. Go check out biomedical.com. Why can't I hear myself? Oh, yep, that's fine. I'm using the correct microphone as well, which is a good bonus. There's obviously no sound engineer, so I have to do everything myself, unfortunately. But luckily, we do have the robot, so I just had 500 subscribers on YouTube like a second ago. I was about to say, let's celebrate during this live stream, whatever. But then someone unsubscribed, so I get to celebrate twice. How good is that? Yeah, go check out biomedical.com. There would be a lot of new tools coming shortly to the site. Hopefully you enjoy them as well. We're looking at brain scans. Yeah, luckily we have a lot of open source data sets. Yeah, CC0. It's always obviously we acknowledge, the authors and everything. Yeah, how to acknowledge? Yeah, we have to do that. This is it. Open fMRI dataset. Here are the authors. A Nature paper, which is always good to see. Is it open source as well? Yeah, open access. Well, that just unfortunately means that the authors had to pay a very large sum to Nature to actually make the paper open source. It's actually surprising it doesn't have any MRI scans in the paper itself. But I guess that's what this dataset is for. And it's available to the public. You can download UCLA something, great stuff. Interesting, and that's what we asking the bot at the moment. Is it also has a functional MRI in it as well. Interesting. I haven't actually seen a functional, and well, never looked at it really. I thought it would be actually looking slightly different than this. So I don't know, there's spikes there. I don't know what actually this means. I suppose this is obviously time, and this is the recording on the same voxel, same area in the brain over time. You can see a low resolution image, and yeah, and it's a bold MRI, so it's focusing. I guess I'm not an expert in this. I'm actually have expertise in cochlear implants and EEG brainwaves recordings, but not MRI. Well, not yet. So that's what we are here for. So I guess when you scroll through this thing, you see how the blood is moving through the brain. So you can see something there, for example, flickering, and that would be the magnetic resonance tomography thing. Wave, a magnetic field is being reflected off blood, and you can see the interior should be able to see oxygenated, non-oxygenated blood. I don't see much in this. Looks highly unusual. Like low resolution image. I don't know why. I'm sure there's a lot of data in it. How big are those files? Yeah, so the good thing about it, you can just download the file. It's only 40 megabyte size. That's interesting. So I have a couple of examples of those. A regular MRI is only 11 megabytes. So essentially, after that one would have a high resolution, something over time. Yeah, that's why the files are larger, but I'm not sure, is it only low resolution like this in the viewer, or is it the actual data? It's nice that you can scroll with your mouse. And that's supposed to tell you something about that specific point. So here, for example, boop, there's some artifact. You can also, with those X's, you can actually see, isn't it obscuring the view? I don't know why the brain is moving. Well, I know why, because it's a living patient, hopefully. And yeah, moving quite a bit. So that's essentially would be some sort of artifact. Here you can see a lot of artifact in that in there. It's just if I don't run out of voice and things to say, we will be using the robot. Just go over some interesting bits. So we're doing a Flask application down this area.
In neuroimaging, structural and functional imaging are two fundamental approaches used to study the brain. They serve different purposes and provide different types of information. Structural imaging. Overview. Purpose. Structural imaging focuses on the anatomy of the brain, providing detailed images of brain structures. Techniques. Primarily used to visualize the shape, size, and integrity of brain regions and tissues. Key techniques. 1. MRI magnetic resonance imaging. Description. Uses strong magnetic fields and radio waves to produce high-resolution images of brain structures. Uses. Ideal for studying brain morphology, detecting structural abnormalities, e.g. tumors, atrophy, and mapping brain anatomy. High spatial resolution, non-invasive, and provides detailed anatomical images. 2. CT, computed tomography, uses X-rays to create cross-sectional images of the brain. Uses. Often used in emergency settings to detect acute brain injuries, bleeding, and fractures. Advantages. Quick imaging, good for detecting acute conditions, less expensive than MRI. Disadvantages. Lower spatial resolution compared to MRI, exposure to ionizing radiation. 3. DTI, diffusion tensor imaging. Description. A type of MRI that maps the diffusion of water molecules in brain tissue, highlighting white matter tracts. Uses. Studying white matter integrity, connectivity between brain regions, and conditions affecting white matter, e.g., multiple sclerosis. Advantages. Provides insights into brain connectivity, useful for studying neural pathways. Structural imaging applications. Diagnosing neurological conditions, e.g., Alzheimer's disease, brain tumors. Pre-surgical planning. Studying brain development and aging. Researching brain anatomy and structural changes related to diseases. Functional imaging. Overview. Purpose. Functional imaging focuses on brain activity and function, showing how different brain regions are activated during specific tasks. Techniques. Used to observe brain activity, study brain function, and map functional areas. Key techniques. 1. fMRI, functional magnetic resonance imaging. Description: measures brain activity by detecting changes in blood oxygen levels, BALD signal, related to neural activity. Uses: mapping brain function, studying cognitive processes, and investigating brain activity related to tasks or stimuli. Advantages: high spatial resolution, non-invasive, can localize brain activity with good precision. 2. PET, positron emission tomography. Description: Uses radioactive tracers to visualize metabolic processes in the brain. Uses studying brain metabolism, detecting abnormalities in brain function, and researching neurochemical processes. Advantages provides metabolic and functional information useful for studying neurotransmitter systems. Disadvantages exposure to radiation, lower spatial resolution compared to fMRI, expensive. 3. EEG, electroencephalography. Description measures electrical activity of the brain through electrodes placed on the scalp. Uses studying brain waves, diagnosing epilepsy, and monitoring brain activity in real time. Advantages high temporal resolution, non invasive, portable. Disadvantages lower spatial resolution, primarily measures cortical activity. 4. Magnetoencephalography. Description measures magnetic fields produced by neuronal activity. Uses mapping brain function, studying neural oscillations, and investigating brain connectivity. Advantages high temporal resolution, better spatial resolution than EEG. Disadvantages expensive, limited availability. Functional imaging applications researching cognitive functions, e.g., memory, language, attention, studying brain disorders, e.g., schizophrenia, depression, mapping brain activity for surgical planning, investigating neural mechanisms of sensory processing and motor control. Combining structural and functional imaging, multimodal imaging. Description combining structural and functional imaging techniques provides a comprehensive view of the brain, integrating anatomical and functional information. Uses enhancing the understanding of brain structure function relationships, improving diagnostic accuracy, and providing detailed maps for research and clinical applications. Examples combining MRI with fMRI for studying how structural changes relate to functional alterations in diseases like Alzheimer's, or combining DTI with fMRI to investigate the connectivity and function of brain networks. Conclusion structural imaging provides detailed anatomical information essential for diagnosing and studying brain morphology. Functional imaging reveals brain activity and function, crucial for understanding cognitive processes and brain disorders. Together, they offer a powerful approach to studying the brain, allowing researchers and clinicians to gain insights into both the structure and function of the brain in health and disease. Current applications in libraries for loading DICOM and NIfTI files. There are several applications in libraries that can load and visualize DICOM and NIfTI files. These tools are used for various purposes, from clinical diagnostics to neuroimaging research. Here are some of the most popular ones. Applications for when working with medical imaging data, particularly in the context of MRI scans, two common file formats are DICOM and NIfI. Here's a detailed comparison of these formats. DICOM, Digital Imaging and Communications in Medicine. Overview, Standard. DICOM is the international standard for medical imaging data. Usage, widely used in clinical environments for storing and transmitting medical images and related information. Data, contains not only image data but also extensive metadata, including patient information, scan parameters, and more. Features, format, DICOM files typically have a .dcm extension. Metadata, rich metadata support, including patient ID, scan details, equipment information, etc. Interoperability, supported by most medical imaging equipment and software, facilitating data sharing across different systems. Structure, can store multiple images, slices, in a single file or as separate files for each slice. Advantages, comprehensive, encodes both image data and extensive metadata, which is crucial for clinical workflows. Interoperable, universally recognized and supported in the medical field. Disadvantages, complexity. The format's complexity and the abundance of metadata can make it cumbersome to handle for non-clinical applications. File size, often larger due to the embedded metadata. NIfTI, Neuroimaging Informatics Technology Initiative. Overview, Standard. NIfTI is a standard format for neuroimaging data, particularly in research settings. Usage, commonly used in neuroscience research for storing processed brain imaging data. Data, primarily focuses on storing the image data with essential metadata related to the imaging. Features, format. NIfTI files have .nii or .nii.gz extensions. The .nii.gz format is a compressed version. Metadata contains essential metadata required for neuroimaging analyses, but less detailed compared to DICOM. Structure typically stores the entire 3D or 4D volume in a single file, simplifying file management. Advantages: simplicity, easier to handle due to less complex metadata. Efficiency, usually smaller in size, especially when compressed. Research-friendly, tailored for neuroimaging research applications, integrating well with analysis tools like SPM, FSL, and AFNI. Disadvantages: limited metadata, contains less detailed metadata, which may be insufficient for clinical purposes. Less interoperable, not as widely supported in clinical environments compared to DICOM. Use cases in your application. When to use DICOM. If your application involves acquiring raw MRI data directly from medical imaging devices. If you need detailed metadata for clinical use or advanced analysis. If interoperability with clinical systems is required. When to use NIfTY. If you are working with pre-processed brain imaging data for research purposes. If you need a simpler, more compact format for neuroimaging analysis. If you are using standard neuroimaging tools and libraries that support NIfTY. Conversion. Tools. Software tools like DCM-TuneIX can convert DICOM files to NIfTY format. This is useful if you start with DICOM files but need NIfTY for specific analyses or visualization tasks. Example command to convert DICOM to NIfTY using DCM-TuneIX. Bash DCM-TuneIX-zy-o output directory input directory. Considerations. When converting, ensure that the essential metadata required for your application is preserved. Choose DICOM if you need the detailed metadata and interoperability essential for clinical use. Opt for NIfTY if you focus on neuroimaging research and need a simpler, more efficient file format. In many cases, you might start with DICOM for initial data acquisition and convert to NIfTY for subsequent analysis and visualization.
Okay, so I have the project file structure, which is great. We'll have a couple of nifty scan file examples in it. Have 3GS for 3D rendering, a orbit control, handling user interactions. That should be fine. I think I used it before, maybe not. We'll see if it actually works. If the bot seems to know quite a bit about it, we'll just go with that. Yeah, so we're doing a Flask application, so we can actually serve it to users on a existing server. And what else? Yes, this is good Flask where we don't actually have anything in it. That's a good start. Because we primarily trying to rely on JavaScript. The HTML is a bit odd. I mean, it doesn't have a canvas. Or does it? No, don't see one. The JavaScript. Okay, can you describe the code quickly? Make sure. So can you confirm that there is not much happening in the backend of the Flask application? Also, is there a need for a canvas in HTML? It looks like it's not there. So if that's will still work, that's okay. We generally would like a description of the application and some general details, science behind it, so on and so forth, at the bottom of the HTML page. Also, any chance you could just put everything into one HTML file to begin with? Yeah, because the just pop them. We'll be using GitHub Copilot in a second as well. We'll just set up the files. The by and the index HTML. So the app file is just simple. There's not much happening in the backend. That also means when you using it, the data is not sent to the server, which is important to us because we want to save electricity. Yeah, the container is holding the 3D viewer. A object loader, pre-computed 3D brain model. Okay. So we essentially, potentially, it's only 72 lines of code using 3GS orbit control. Now the question, It's not constructor. Live reload enabled, that's good. Yeah, I'll quickly touch. Okay, can you quickly explain the code just in text alone? Don't generate any new code. Also, can you touch on the difference between running it as a Flask application as opposed to the HTML by itself? Would the HTML doesn't require anything else to run? And if I'm running the Flask file, is it just calling the HTML? I think spelling mistakes is fine. It didn't give an overview for the code, it's just more on the technical side, which is okay.
Code explanation. HTML structure and JavaScript integration. HTML, the div ID container, is where the 3D scene will be rendered. The style tag ensures that the container takes up the full viewport. The script tags load Three.js and orbitcontrols.js libraries from a CDN. The JavaScript code initializes the 3D scene, camera, renderer, and controls, loads a 3D model, adds lighting, and sets up the render loop. JavaScript, 3.js setup, creates a 3-dot scene to hold all 3D objects, configures a 3-perspective camera for viewing the scene, sets up 3.webgl renderer to render the scene and attaches it to the attached container div. Controls, 3-to-orbit controls, enables interactive controls, rotate, zoom, pan for the camera. Model loading, 3.object loader load loads a pre-computed 3D brain model, assumed to be in JSON format, and adds it to the scene. Lighting adds ambient and directional lights to illuminate the model. Animation loop, a function animate continuously updates the controls and re-renders the scene, enabling real-time interaction. Responsive design, an event listener adjusts the renderer and camera aspect ratio when the window is resized. Running as a Flask application versus standalone HTML. Standalone HTML. The HTML file can be opened directly in a web browser without any additional setup. Pros, easy to run. Just open the file in a browser. No need for a server or backend processing. Cons, limited in terms of backend capabilities, e.g. handling user uploads, processing data server-side. Running as a Flask application. The HTML file is served by a Flask application. How it works. The Flask application runs a server that listens for requests and serves the HTML file when accessed. Pros, can handle backend processing, such as serving different files, processing user input, or interfacing with a database. More scalable for adding complex features in the future. Cons, requires setting up and running a Flask server. Slightly more complex setup compared to just opening an HTML file. Flask code explanation. app.py imports Flask and sets up a basic Flask application. Defines a route at app.route/ to serve the index.html file. When accessed, Flask renders the index.html template. The application runs a local server, app.run debug equals true. Hash summary. Standalone HTML, simple, quick to run, no dependencies. Just open the HTML file in a browser. Flask application, more powerful, can handle backend tasks. Requires running a Flask server, which serves the HTML file. Both approaches will display the 3D brain model viewer, but using Flask allows for more advanced features and scalability if needed in the future.
Yes, obviously, we'll be doing a Flask application, so that means we can't have, yeah, we won't be running the HTML like this. no point doing that. We need to fix those errors though. Why do we need the 3JS locally? Yes, it's corrected. It's only 72 lines of code. Yeah, it's really tempting to just do right. So the model meant to be in a JSON file. Yeah, we don't currently have it. Yeah, might have to stick to Flask. If it's suggesting all these files, can it actually generate them? Yeah, we'll go with Flask application. And yeah, let's actually open it in a new Visual Studio window and folder. Yeah, we're calling it Brain 3D. Have this info index HTML meant to be in the template folder, isn't it? Render template. Yeah, the port is already in use. We have to close the other one. Have to close. Try running it again. Meant to be templates, is it? Right. Let's see. Yeah, we don't have the model. We don't have the model. Okay, let's bring up pop in actually place it in there. Where's the JSON brain model? Don't get it. Yeah, the files are there, templates, that's right. Let's just play it down and just populate all this stuff for now. Okay, we don't actually have that code that generates the JSON file. Hey, can you actually explain the code? Specifically, where do we have the bit, or do we have it at all, that generates the brain model JSON file? Is it generating it out of the data imaging file? Don't, so it didn't generate that code to. Yeah, it's assuming we have that model. Well, we do not. Generating three brain models JSON file. Okay, so we have this Python code. This wouldn't work, would it? Dumping the model. Yeah, we don't necessarily want an upload function at this stage. Okay, there's a couple of issues. We don't want an upload function at this stage. I don't think my server has the capacity to deal with uploads at the moment. Now we want to process existing data examples. So we want to be able to view them first, the original image slices, scrolling through them, the different orientations, and a simple 3D model as well. So essentially, the standard for canvas window. Also, we would like to rely on JavaScript as much as possible. So essentially, leaving the backend not doing anything at this stage, or doing something only if absolutely necessary. Let's see if it will restructure the thing or not. Changing the folder structure. Well, anyhow, one thing is for sure, we'll need a static folder. Yeah, forget the logo. We don't need a logo at this stage.
Given your requirements, we can focus on creating a JavaScript-heavy solution that processes and visualizes pre-existing MRI data examples. We'll implement a basic viewer that allows you to scroll through image slices in different orientations and view a simple 3D model of the brain. The backend Flask will only serve the static files and handle minimal necessary tasks. Steps. 1. Prepare MRI data. Ensure you have pre-computed MRI slices and a 3D brain model in suitable form.
Just happened and had an error reading the text. Yeah, I'll need to update the description at the bottom of the page anyway. So if it's loading the script from Ajax, well, from Cloudflare, why do I need it stored locally as well? It's a bit odd. Can you give a quick overview of the code? Also, why do we need the JavaScript files locally if we are using a CDN, also in future responses, when you generate code, can you generate all the text first and the code at the bottom of the response? This is because I'm using text to speech to read out your responses. And I don't want the code coming up at the top. By the way, while it's generating, go check out biomedical.com. This is the most recent tool, and there was a few questions, complaints about it, which we would like to address. Well, first, the color, the background, whatever. Yeah, we don't care. If you have any other color suggestions, do let me know, but you'll have to explain why this color is no good in details. Now, yeah, so the number of electrodes can change, but yeah, someone was saying that it's only activating the first, whatever, half of the electrodes. The reason being, I already mentioned it before, is that I'm actually testing with a bad microphone, which supposedly has a big range. So if I mute my microphone so I don't blow your ears and actually do like a hissing sound or something. Yes, this is what I get when hissing and effing into my microphone's kind of mid-range, I don't know, $150 kind of mic. Yes, I understand in your phone or earbuds you will have a different microphone. So if you can reach the higher frequencies and deeper electrodes, shallow electrodes or deep, no, yes, high frequency electrodes, you can try the filter, particularly the high pass. So if you place the high pass, it should remove the lower frequencies. If you keep going, hopefully your microphone can still pick up something. It's probably not a high quality audio, but you could see how the implant is activated in the higher frequency electrodes. You can drive it even higher. And again, if I hiss and do stuff, just turn my audio off for a sec. Yeah, just make sure you turn the low pass off to see anything at all. And yeah, you might get something in your high frequency electrodes. So try that out. Okay, so it's reach. It's actually did what I asked for, generating the text first.
Overview structure. The HTML structure sets up 4 canvas elements to display different views of MRI data. Axial view, horizontal slices. Sagittal view, vertical slices from left to right. Coronal view, vertical slices from front to back. 3D view, a 3D model of the brain. Each canvas is contained in a div with a class canvas container to ensure they are properly sized and positioned. JavaScript functionality, 3 setup for
Why did it fail to play the audio for? That's not cool. Let's try again, or have something heavy loaded in the browser. Yeah, the problem with this tool, yeah, so it's an amazing tool. It's called brainchop.org, available for free on the site. It has amazing models in it and stuff, but they're quite heavy. So I can't, yeah, it says memory okay, but it's actually using quite a bit of my GPU. I was testing it before, it was getting up to like, and I have a very powerful GPU, and it's quite a heavy, becomes unresponsive. Well, I mean, and I can't do much with my other things with my browser. So this is nice. However, there's a weird... What's this thing? Not sure why this was it pink? Things are still showing when in this point. So this is not the original example image that came with the tool. I'm not sure. Yeah, there's some pinkish thing here. It's I think it's mislabeling stuff over there. The whatever color this is, yellow, meant to be across all that bit. Then there's pink there, which makes sense. You see, we are in the pink region on all in all directions. There's a weird. So when we are here, for example, yeah, we start seeing pink. Wait, I'm a bit confused. Yeah, there's the same thing with the 3D model. When you clip it, it's always clipping in the same area. So I'm not sure what's up with that. Yeah, the models are great. I mean, they're not high resolution. I mean, the original image is not high resolution. Yeah, you saw that bit before was not labeled. Yeah, this is kind of, yeah, the 3D model is a bit useless. Yeah, this is nice. Yeah, but that bit here, yeah, we see the pink, and it should not be there. I think. Not entirely sure what's going on. Yeah. Yeah, there's pink there, so that meant to be this slice, right? When you're down the bottom here, oh no, I think it's okay. And no, no, Yeah, a bit confused. Anyway, I don't know much about this. Should just make sense, should it? Nah, it should be fine. Sorry, made a mistake. It's yeah, it's essentially this. No, yeah, it's okay. Yeah, I'm still not sure about the. Yeah, so I made a mistake with the pink bit is fine. I wasn't in the correct location. I still think this one is mislabeled a bit. Yeah, it doesn't seem to be labeling the whole thing. Anyway, if you load the original, I want to see this is what the image and then the model goes away. Yeah, we could be saving the model in the browser if it was already loaded, for example. So I have some sort of thing that tells you which model was already loaded or processed and loaded from existing memory. Yeah, so now it's processing. It's taking quite a bit of my. It's done. That was quick. High memory fast. Okay. Yeah, this one's labeling better. Yeah, so it's working better with the. Seem to work better with the example as opposed to another image. I don't know what's jumpy like that. It's the text here. When you have two lines, then the image is jumping. That's kind of minor a thing to fix. Yeah, it's hard to get the hang of navigating it. Yeah, this probably should be labeled with something as well. But yeah, the example is working, seem to work a bit better than. Yeah, how is it labeling that? There's like nothing in the well. Yeah, anyway, it's very interesting to say the least. To have some questions about it. And also, so essentially trying to do something. We'll close this one for now. Yeah, we'll have this open source data. So this is Creative Commons 0, so just public domain. And we're using those images. And be trying to web data HTML32 lines. That's the same. Yeah, I'm not sure. So why are we generating all the, why do we need all the images in a static folder? Wouldn't be just loaded from the data file? Please explain. Yeah, we'll generate the code at the end of this prompt, wouldn't it? Yeah, it has to generate all the text first. It doesn't do that.
Serve pre-computed images from the static directory for simplicity and quick access. Dynamic loading. Use Flask to dynamically serve image slices from a Nifty file if real-time processing is needed. JavaScript handles rendering and navigation of MRI slices on the client side, reducing the load on the server. Serve pre-computed images from the static directory for simplicity and quick access.
Okay, that's now just reading the last bit, the one that continued generating instead of the whole thing. Yeah, the whole website is a bit buggy, but that's okay. Backing code to serve slices from Nifty file. Oops. Yeah, this is something GitHub Copilot can solve for us. It's the missing library thing. Yeah, we don't have data, do we? But why there's no error? And this 20 it's really weird that there's no error. Yeah, this bit. So we should have in a static folder. Have a null folder called data and let pop. We just download. Yeah, those are compressed. Just pop in some earlier ones. No, we don't want to open them in file and folder structure. Quickly use Copilot a workspace. Just update updated file and folder structure. Yeah, this is kind of what we might have at the end, but this is what we currently have. Yeah, the README will be just at the bottom of the HTML page. Yeah, we need the workspace date this. Let's see if it can do it. And it's a bit odd. No, we don't. Don't have that file. Why is it? Just do it manually. A copy relative path. The no errors. Nothing is displayed. It's a bit. Don't understand. Yeah, we don't have that model. Currently have this. Yeah, while it's generating, go check out biomedical.com. Any comments, suggestions, complaints? Welcome. Yeah, that's better for, I don't know why it's was trying to pop in the HTML code into the Flask backend. Right, this looks like the legit folder. HTML. JavaScript, does it still have the images? I hope not. Yeah, we do see data. And again, loading quite slowly. Okay, a couple of things. It's loaded something, which is great, but it's a bit slow. I'm not able to flick through the slices. The 3D model is not there, and we are also missing a description at the bottom of the HTML. Now remember, when generating responses, can you place all the text first, including the summary of the response? And if there is any code, place it second. So why can't do basic instructions? And there's well, the model is not there. We actually need to generate it. So how do I move? Slice. It's moving through. Yeah, it's actually moving through slices. Yeah, caching. That's the key to success. Maybe not. Adding description. If anything, it should have improved the code. It's not able to generate a whole lot.
Current coronal index, coronal context. Summary, performance, improved by caching slices once loaded and optimizing rendering. 3D model, ensured the 3D model is correctly loaded and added error handling. Description, added a description at the bottom of the HTML page. Error handling, addressed missing files and server errors. This setup should provide a more responsive interface and correctly load both the 2D slices and the 3D model with additional descriptions and error handling in place.
Navigate with arrows. Yeah, up and down through axial. Yeah, might need the terminal. Errors from the Python terminal as well. Don't know why there's so much happening at the back end. The data is static. Yet the model, the 3D model, should be just generated once. Okay, a couple of things. First, can we fix the display? Make sure that the images fit better on the front page. Now the question is, well, there's multiple questions. First of all, can we just generate the 3D model on the server and have it as a static file? So when the example scan is served to the user, everything is already in place. Also, another thing, can we improve navigation through the slides? Currently it's only arrows, I think, but if we can add the mouse functionality, that would be awesome. Keyboard.
Overview of the application. Application name, 3D Brain MRI Viewer. Description: the 3D Brain MRI Viewer is an interactive web application designed to visualize and explore MRI data of the brain. The application allows users to view 2D slices of the brain in different orientations, axial, sagittal, and coronal, and interact with a 3D model of the brain. Features: 2D Slice Viewer. View MRI slices in axial, sagittal, and coronal orientations. Navigate through the slices using keyboard arrows or mouse wheel. 3D Model Viewer. Interact with a 3D model of the brain that can be rotated, zoomed, and panned using mouse controls. Educational Tool. The viewer is designed for educational purposes, providing a detailed look at the brain's anatomy. Use cases: medical education. Useful for students and professionals to learn about brain anatomy. Research. Assist researchers in visualizing and analyzing MRI data. Patient education. Help patients understand their own MRI scans in a more interactive way. Instructions for use. 1. Viewing 2D slices. Keyboard navigation. Use the arrow keys to navigate through slices. Up-down arrows. Navigate through axial slices. Left-right arrows. Navigate through sagittal slices. Page up, page down. Navigate through coronal slices. Mouse navigation. Use the mouse wheel to scroll through slices on each canvas. 2. Interacting with the 3D model. Rotate. Click and drag the mouse to rotate the model. Zoom. Use the mouse wheel to zoom in and out. Pan. Click and drag with the right mouse button to pan the view. Development process. Backend, Flask. The backend is built using Flask and serves the HTML template and static files. It also includes routes to dynamically serve MRI slices from an INIFTY file. Frontend, HTML, CSS, JavaScript. The frontend uses HTML and CSS for layout and styling. JavaScript with 3JS is used to render the 3D model and manage interactions with the 2D slices and 3D model. MRI data processing. MRI slices are extracted from a NIFTY file using Nibable and served as images. A 3D model is pre-computed from the MRI data and served as a static JSON file. Instructions to add to HTML. Updated HTML with description. HTML, docs.html, tmeta charset UTF-8, head, meta nameplate with viewport, content with device width, initial scale 1.0. Title: 3D Brain MRI Viewer. Link rel style sheet fref. File name equals css styles.css. Style body, margin 0. Display flex, flex wrap wrap. Canvas container, flex 1. Width 50%. Height 50 VH. Box sizing border box. Padding 5px. Canvas width 100%. Height 100%. Border 1 pix solid DD 100%. Text align center. Padding 1m. Background hatchad F0 FEO. Div class canvas container. Canvas ID canvas. Canvas ID sagittal view. Canvas ID canvas coronal view. Script canvas 3D view. Scripts are ap/cdn.js.cloudflare.com/aj/lib/3.deliver.net/3@point121.8.nero/example/js controls/orbit Script searching and a URL for static, file name equal js/main.js. Footer strong application overview. This 3D brain MRI viewer allows users to explore the brain's anatomy interactively. Using MRI data, the application generates 3D models that can be rotated, zoomed, and panned. Users can view various brain structures, such as the cerebrum, cerebellum, brainstem, and ventricles, in different orientations: axial, sagittal, coronal. This tool is designed for educational purposes and utilizes advanced web technologies like 3JS for rendering the 3D models. The MRI data is pre-processed to label brain structures and generate models, ensuring a balance between model size and accuracy. Strong scientific background. MRI, magnetic resonance imaging, is a non-invasive imaging technology that produces three-dimensional detailed anatomical images. It is often used for disease detection, diagnosis, and treatment monitoring. The application uses 3JS, a powerful 3D library that makes WebGL easier to use for rendering the MRI data as interactive 3D models. Instructions: viewing 2D slices. Use the arrow keys to navigate through slices. Up-down arrows, navigate through axial slices. Left-right arrows, navigate through sagittal slices. Page up, page down, navigate through coronal slices. Use the mouse wheel to scroll through slices on each canvas. Interacting with the 3D model. Rotate. Click and drag the mouse to rotate the model. Zoom. Use the mouse wheel to zoom in and out. Pan. Click and drag with the right mouse button to pan the view. Development process. The backend is built using Flask and serves the HTML template and static files. It also includes routes to dynamically serve MRI slices from a Nifty file. The front end uses HTML and CSS for layout and styling. JavaScript with Three.js is used to render the 3D model and manage interactions with the 2D slices and 3D model. MRI slices are extracted from a Nifty file using Nibable and served as images. A 3D model is pre-computed from the MRI data and served as a static JSON file. Hash summary. Overview describes what the application does and its features. Instructions provides usage instructions for navigating the 2D slices and interacting with the 3D model. Development process outlines how the application is built, including the backend, front-end, and MRI data processing. This detailed description can be added to the footer of your HTML page for user reference.
What I currently have, it's a zip file of the whole project directory. Keep getting a lot of errors as seen in the image attached. The 3D model was generated, but there are issues loading it, parsing it.
Overview of the current application issues. Based on the screenshot and the provided zip file, there are a few issues. 1. 3D model parsing error. The 3D model JSON file has a syntax error or is not properly formatted. 2. Internal server errors. The Flask backend is encountering errors while serving image slices. Steps to resolve. 1. Fix the 3D model JSON file. Ensure the JSON file is correctly formatted and valid. 2. Debug internal server errors. Investigate and resolve the server-side errors related to serving image slices. 1. Fix the 3D model JSON file. Let's start by checking the 3D model JSON file to ensure it is correctly formatted. Check and correct the JSON file. Open the JSON file. Use a JSON validator or an editor with syntax highlighting to check the brainmodel.json file for errors. Correct the structure. Ensure that the JSON file is correctly formatted. Example of a correctly formatted JSON file. JSON metadata, format version 3.1, type geometry, generated by JSON.3, vertices 8, faces 6, normals 0, colors 0, UVS 0, materials 0, morph targets 0. Vertices 1, 1, nice 1, 1, nice 1, 1, 1, nine 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1. Faces 0, 0, 1, 2, 3, 0, 4, 7, 6, 5, 0, 3, 7, 4, 0, 0, 1, 5, 6, 2, 0, 0, 0, 1, 4, 5, 0, 2, 6, 7, 3. Debug internal server errors. Ensure the Flask server correctly rereads and processes the Nifty files. Check the Flask route. Verify that the serve slice route correctly handles the slicing of the Nifty file and that the file path is correct. Fixing the Flask route. Python from Flask, import Flask, send for file, render template, JSONify, import nibble as nib, import numpy as np, import matplotlib.pyplot as plt, import ioapp equals flask at app.route slash, def index, return render template index.html at app.route slash slice annotation index, def serve slice orientation index, try nifty file equals static.
Can you summarize the changes made? Also touch on the whole structure. So my current understanding is that I'm pre-processing the data files on the server, so it's nothing to do with the user. Then the model is created and the images are created. So both the 3D model and the images are statically served on the page, so front end. Can you actually check the wait, there was another Python code that was generating the 3D brain model out of the scanner data. Hey, where is that file? Where is that file? Hopefully it won't start generating more code. I'm pretty sure I have enough code. No, I thought it will move the data outside the static folder. There's okay, pre-process. Okay.
Summary of changes and project structure. Changes made. 1. Fixed the display, adjusted the CSS to ensure images fit better on the front page. 2. Generated the 3D model on the server, added a script to pre-process the Nifty files and generate a 3D model JSON file. Ensured the JSON file is correctly formatted. 3. Improved navigation, added mouse-based navigation for scrolling through image slices. 4. Added description to HTML and included a detailed description at the bottom of the HTML page explaining the application, its features, instructions for use, and the development process. Current project structure. The project is structured to pre-process MRI data on the server, generate the necessary static files, and then serve these files to the front end for visualization. The user interacts with the pre-processed static files without the need for additional back-end processing. /brain3d app.py flask application info.txt. Additional information about the project, static files served by flask css styles.css css styles sub 0 sef t1wni nifti files sub 01 t1w.ni t1 crop.na main.js JavaScript for front-end functionality models brain model.json pre-computed 3D brain model /images tagger placeholder for additional images if needed templates, index.html or html preprocess.py script top preprocess MRI data and generate 3D model. Preprocessing script. The preprocessing script reads the NIFT files, extracts the necessary slices, and generates the 3D model. This script is run on the server to prepare the data before it is served to the user. Preprocess.py. Python import nibble as nib. Import numpy as np, import JSON, import osdef generate 3D model nifty file, output file, img equals nib.load nifty file, data equals img.getf data, vertices equal, faces equals, for I in range data.shape 0, for j in range data shape 1, for k in range data shape 2, if data ijk0, threshold to determine presence of tissue vertices, append ijk. For I in range len vertices nice 1, faces.append I plus 1, I plus 2. Model data equals metadata, format version 3.1 type geometry, generated by JSON.to3, vertices len vertices, faces, normals 0, colors 0, UVS 0, materials 0, morph targets 0. Vertices, vertex and vertices for chord and vertex, faces, face for face and faces, with open output file w as f json.dump model data f. Generate model, run this once. Nifty file equals static /0 sest11w.nii. Path to the Nifty file, output file equals static model /brain model.json. Output path for the 3D model, generate 3D model, Nifty file, output score file. Explanation of the preprocessing script. Function generate 3D model. Input, path to the Nifty file and the output JSON file path. Process, loads the Nifty file using Nibabel. Extracts 3D coordinates of brain tissue based on a threshold. Generates vertices and faces for a simplified 3D model. Formats the data into a JSON structure compatible with 3JS. Saves the 3D model as a JSON file. Flask application. app.py. Python from Flask. Import Flask, send file, render template, JSONify. Import nibable as nib. Import numpy as np. Import matplotlib.pyplot as plt. Import io. Import os app equals flask name. app.route def indexix. Return render template index.html. Add at peep.route //// orientation / def serve slice orientation index. Try nifty file equals static data / sub 0 ses -1t1.nii. Update with the correct file path. img equals not load nifty file. Data equals img get f data. If orientation equals axial, slice data equals data index. Elif orientation equals sagittal, slice data equals data index. Elif orientation equals coronal, slice data data index. Else return invalid orientation. 400, slice data equals np.rot90, slice data. Rotate the slice if needed for correct orientation. Fig x equals plt.subplots, ax.imshow slice data cmap equals gray, ax.axis off, buff equals io.bytes io, pl.save fig buff format equals png, pl.close fig buff.seek 0 return send file buff mime image png. Accept exception as e, return JSONify error star e, 500 add app.route /model, def serve model, model path equals static models brain model.json. If os.path.exists model path, return send file model path. Return JSONify error model not found. 404 if the name equals score main. App.run debug equals true. Key points, preprocessing, performed on the server using preprocess.py. Serving static files. Once preprocessed, the 3D model and MRI slices are served as static files. User interaction. Users interact with the preprocessed data through the web interface. This structure ensures efficient data processing on the server side and seamless interaction on the client side, making it suitable for educational and research purposes.
Yeah, there's still something wrong. Can't load the model for whatever reason. And let's read the response quickly.
Summary of issues and fixes. 1. Unexpected end of JSON input. The brain model.json file is not correctly formatted or is incomplete, causing the object loader to fail when parsing it. 2. Internal server errors. Confirm the server handles MRI slices correctly. Steps to fix. 1. Ensure correct JSON formatting. Validate and correct the JSON format in the brain model.json file. 2. Revalidate preprocessing script. Ensure the preprocessing script generates a complete and valid JSON file. 3. Verify and debug Flask routes. Confirm the server routes are functioning correctly without errors. Correcting the 3D model JSON. Let's first ensure that the preprocessing script correctly generates the JSON file. Here's the updated script with additional checks and a simplified structure for clarity. Preprocess.py.
So if we have to run it again. So currently it's like 585 megabytes. Let's see if we run it again, if it will change at all. It shouldn't. It is the model in the 3D model is in the original data. So we're creating our own. That wouldn't make much sense. Maybe it will later or something. Right, now it's much smaller. So what's up with that? Still running though. Didn't finish. Three on 905. Let's try this again. Yeah, 3 on 905 megabytes. So the model have changed. Front end seem to be the same. Okay, we need to actually run the app. Yeah, not load the model. Why? There's something wrong with that model, is there? Can't load model. Coming from it's different errors. We might try this again. Need to troubleshoot this. Any chance the model is included in the original data, the 3D model? Yeah, I'm just going in circles. Going in circles. Yeah, I have to tell it to use a different approach, or, well, the easy thing would be to just work on something else.
Checking for pre-existing 3D model in original data. It's possible that the original Nifty file contains data that can be used to generate the 3D model directly. Typically, Nifty files contain volumetric data, which represents 3D structures. This data can be processed to visualize 3D models without having to manually create vertex and face lists. Steps to verify and use the original data for 3D model. 1. Check the Nifty file. Examine the Nifty file to understand its contents and see if it contains pre-existing 3D model data. 2. Generate 3D model from volumetric data. Use the volumetric data to generate a 3D model directly. Verifying Nifty file. First, let's inspect the Nifty file to see what kind of data it contains. You can use nibable to load and visualize some basic properties of the file. Inspecting the Nifty file. Python import nibable as nib. Load the nft file. Nifty core file equals /data sub 0 ses -1 t1 dub ni. img equals nid.load nifty file. Print header information. Print img.header. Print shape of the data. Data equals img.getFdata. Print generating 3D model from volumetric data. If the Nifty file contains volumetric data, you can use tools like SkimAge and marching cubes to generate a 3D surface model from the volumetric data. Example script to generate 3D model. Python import nibable as nib. Import numpy as np. Import JSON from SkimAge. Import measure. Def generate 3D model from volumetric data, Nifty file, img equals nib.load Nifty file. Data equals img.getFdata. Apply threshold to generate a binary volume, verts, faces, normals, values equals measure.marchingcubes data, level equals 0.5. Model data equals metadata to generate the model. Check Flask routes. Confirm the server routes correctly serve MRI slices and the 3D model. Test frontend. Ensure the JavaScript frontend loads and displays the 3D model and MRI slices correctly. By following these steps, you should resolve the issues and successfully load and display the 3D model along with the MRI slices.
Yeah, so generating the 3D model, supposedly in a different way, should be much quicker. Still about 240 megabytes. Still having the same issue. Can you give an overview of the whole code? Do not generate any new code, just text at this stage. Just give an overview of the whole application and why am I getting these errors.
Overview of the application. The application is a 3D brain MRI viewer that allows users to explore brain anatomy interactively using MRI data. The main components of the application include 1. Flask backend serves the HTML template, static files, and dynamically generated image slices. 2. Pre-processing script generates a 3D model JSON file from MRI data. 3. HTML and JavaScript frontend renders 2D slices and the 3D model, allowing interactive navigation. Detailed breakdown, Flask backend, app.py, responsibilities, serve the main HTML page, provide endpoints to serve image slices dynamically, serve the pre-computed 3D model JSON file. Key route slash renders the main HTML template. 2. Slash slice orientation int index dynamically generates and serves MRI image slices. 3. Model serves the pre-computed 3D model JSON file. Errors noted. Internal server error when attempting to serve image slices. Issues loading the 3D model JSON file. Pre-processing script, generate 3D model.py. Responsibilities, load the nifty MRI data. Generate a 3D surface model using the marching cubes algorithm. Save the model data as a JSON file compatible with 3.js. Key steps. 1. Load the nifty file using Nibable. 2. Normalize and threshold the data. 3. Extract surface data using schemage.measure.marchingcubes. 4. Save the model data in a JSON format. Errors noted. Possible issues with the JSON file formatting or completeness. HTML and JavaScript frontend defines the layout of the page, including containers for 2D slice views and the 3D model view. Includes CSS for styling. JavaScript main.js sets up the 3D scene using 3JS, loads and displays the 3D model. Manages interactive navigation for 2D slices and the 3D model. Errors noted. Issues loading the 3D model JSON file, unexpected end of JSON input, internal server errors when fetching image slices. Common causes for errors. 1. 3D model JSON file. Incomplete JSON file. The JSON file might be truncated, leading to parsing errors. Incorrect JSON structure. The JSON structure might not be compatible with 3.js object loader. 2. Flask backend. File path issues. Incorrect file paths or permissions might cause the server to fail when accessing files. Data processing errors. Errors in data slicing and processing can lead to internal server errors. Next steps for debugging. 1. Verify 3D model JSON file. Ensure the JSON file is fully written and correctly formatted. Use a JSON validator to check the file's integrity. 2. Check Flask routes. Add detailed logging to the Flask routes to capture and diagnose errors. Ensure file paths are correct and files are accessible. 3. Debug JavaScript errors. Check the Network tab in the browser developer tools to see the exact responses from the server. Ensure the JavaScript code correctly handles responses and errors. Summary. The application involves a Flask backend to serve dynamic content and a frontend that renders 2D slices and a 3D model using 3JS. The main issues are related to loading the 3D model and serving image slices. Addressing these involves verifying the JSON file, checking server routes, and ensuring correct JavaScript error handling.
A quick response. Did you say the original data actually includes the 3D model?
The original nifty data itself does not typically include a 3D model in the sense of a pre-computed surface mesh. Instead, it contains volumetric data that represents the density or intensity values of the brain tissue in a 3D space. This volumetric data can be processed to generate a 3D surface model. Generating a 3D model from volumetric data. To clarify, volumetric data. The NIFT file contains 3D volumetric data that represents the brain's structure. Each voxel, 3D pixel, in this data represents the intensity value at that point in the brain. This 3D surface model. A 3D surface model can be generated from this.
Okay, we just learning about the MRI data. We haven't processed any before. Can we just first display what the nifty file has in it originally? If it's volumetric data, that's fine. So can we just replace the fourth canvas on the front panel to display the volumetric data? Also, a minor thing, can you make sure the four canvases are arranged correctly on the screen? So
addressing current issues. Volumetric data not displaying. The volumetric data slice is not visible on the fourth canvas. 2. Errors with slices. There are internal server errors when fetching certain slices. Debugging steps. Volumetric data display issue 1. Ensure correct endpoint. Confirm that the correct endpoint is being called for the volumetric slice. 2. Check canvas rendering. Verify the canvas rendering logic in JavaScript. Slice fetching errors 1. Log server errors. Add detailed logging in Flask to diagnose why certain slices cause internal server errors. 2. Validate data. Ensure the slice index does not exceed the dimensions of the Nifty file. Updated JavaScript for volumetric data. Main.js. Ensure correct endpoint and debugging for volumetric slice. JavaScript function fetch and draw volumetric slice. Let img equals new image. Einstcirc equals slice axial slash 0. Initial slice img.onload equals volumetric context.clearrect 0. Volumetric context.canvas.width. Volumetric context.canvas.height. Volumetric context draw image img 0 0. Volumetric context canvas.width. Volumetric context.canvas.height. img.honor equals console.error. An error occurred while loading the volumetric image slice, img tsurik. Fetch and draw volumetric slice. Updated Flask code for detailed logging. app.py, add detailed logging. Python from Flask, import Flask, send file, render template, JSONify. Import nibabel as ndib. Import numpy as np. Import matplotlib.pyplot as plt. Import io, import os app.flask, add app.route/defindex. Return render template, index.html. Add app.route/orientation int index. Def serve slice orientation index. Try nifty file equals statics data sub 01 t1w.nie. Update with the correct file path. img equals init.load nifty file. Data equals img.getFdata. Max indices equals data.shape if index equals max indices 0, or index equals max indices 1, or index weak equals mindices 2. Return JSONify error, index out of bounds. 400. If orientation equals axial, slice data equals data index. Elif orientation equals sagittal, slice data equals data. Elif orientation equals coronal, slice data equals data index. Else, return invalid orientation. 400. Slice data equals np.rot90, slice data. Hap rotate the slice if needed for correct orientation. Fig ax equals pl.subplots, ax.imshow, slice daymac equals gray, ax.axis off, buff equal to io.bytes io, pl.save fig buff, format equals png, pl to close fig, buff.seek 0, return send file, buff mime type equals image/png, accept exception as e, print f error serving slice orientation at index stir e, return JSONify error stir e, 500. If name ape equals main, app.run debug equals true. Hash debugging server errors. 1. Run the Flask application. Start the Flask application and reproduce the errors. 2. Check logs. Examine the terminal or log output to see detailed error messages. Summary of adjustments. JavaScript ensured the correct endpoint is called for the volumetric slice and added error handling. Flask added detailed logging to diagnose errors and included bounds checking for slice indices. By following these steps, you can diagnose and address the issues with volumetric data display and slice fetching errors.
Okay, can you explain something and confirm that the original data should be just in the main folder of the project? Then out of it, we are fetching everything we need for plotting this specific dataset and placing it in static folder. So essentially, we would like everything that is required for rendering the data already being in the static folder, and the pre-processing Python file takes the original data file and gets everything it needs out of it. So in this case, images and the volumetric model.
Explanation and confirmation of data handling and pre-processing. Project structure and data handling. 1. Original data. The original Nifty file is placed in the main project folder. This file contains the volumetric MRI data needed for visualization. 2. Pre-processing. A pre-processing script processes this original Nifty file to extract the necessary data, slices and 3D model, and places the extracted data into the static folder. 3. Static folder. The static folder contains all the pre-processed data, image slices and 3D model required for rendering the data in the web application. Project directory structure. Flash Brain 3D, app.py, Flask application, preprocess.py, pre-processing script info.ext, additional information about the project, sub0set1t1.nii, original Nifty file placed in the main folder. Static files served by Flask, CSS, styles.css, CSS styles, data. Axial, axial slices generated by preprocessing. Sagittal slices generated by preprocessing. Coronal slices generated by preprocessing. JS main.js, hack JavaScript for front-end functionality. Models, brainmodel.json, pre-computed 3D brain model. Placeholder for additional images if needed. /templates, index.html. HTML template, hashtag preprocessing script. The preprocessing script, preprocess.py, processes the original Nifty file and saves the required slices and 3D model to the appropriate locations in the static folder. Preprocess.py, Python import nibbable as nib, import numpy as np, import JSON, import OS from schemage, import measure, matplotlib.pyplot as plt. Def create slices Nifty file output dir, img equals nib.load Nifty file, data equals img.get fdata. Create output directories, they don't exist, os to make dirs output dir, exist equals to OK. Axial dir equals os.path join output dir axial. Sagittal dir equals path.join output digital. Coronal dir equals path join output dir coronal. os.make dirs axial true. os make dirs os exist goes true. os make dirs coronal dir exist okio. Save slices for I in range 2, plt.imsave os.path join axial dir fi png, np.rot90 cmac equals gray. For I in range data.shape, plt.imsave join sagittal dir fi png, np.rot90 cmap equals gray. For I in range data.shape, pl.imsave os.path join coronal dir f.png, np.rot90 mac equals gray. Def generate 3D model, Nifty file, output file, img equal mb data mg.get fdata. Data equals data np.max data. Normalize data for marching cubes. Extract surface using marching cubes, verts, faces, normals, values equals measure.marching cubes data level 0.5. Create model data. Model data equals metadata. Format version 3.1. Type geometry. Generated by JSON.23. Vertices len verts. Faces len faces. Normals len normals. Colors 0. UV is 0. Material gets 0. Vertices verts.tolist. Faces faces.tolist. Normals normals.tolist. Save model data as JSON with open output file W as f, json.dump model data f. If core name equal to main, Nifty file equals sub 0 ses1 t1w.ne. Original Nifty file output dir equals static/data. Directory to save slices model output equals static models/brainmodel.json. Path to save 3D model. Create slices Nifty file output dir. Generate 3D model Nifty file model output. Summary of preprocessing steps. 1. Extract slices. Read the Nifty file. Generate axial, sagittal, and coronal slices. Save the slices as PNG images in the appropriate subdirectories, axial, sagittal, coronal, within static/data. 2. Generate 3D model. Read the Nifty file. Use marching cubes to generate a surface mesh from the volumetric data. Save the 3D model as a JSON file in static/models. Flask backend. The Flask backend serves these preprocessed static files. App pop Python from Flask, import Flask, send file, render template, JSONify. Import os app equals Flask, def index, return render template index.html /slice orientation int index. Def serve slice orientation index, try, if orientation not in axial, sagittal, coronal, return invalid orientation. 400 slice path equals os.path static data orientation f index png. If not os.path exists slice path, return slice not found. 404, return send file slice path. Accept exception as e, return JSONify error stir e. 500 at app.route/model. Def serve model, model path equals static model/brainmodel.json. If os.path exists model path, return send file model path. Return JSONify error model not found. 404 if core name equals score main app.run debug is true. X summary. Original data. Place the original Nifty file in the main project folder. Preprocessing. Use a preprocessing script to extract slices and generate the 3D model, saving them in the static folder. Static folder. The static folder contains all the preprocessed data needed for rendering, image slices, and 3D model. Flask backend. Serves the preprocessed data to the front end for visual equals current sagittal index plus increment 100%. Adjust according to number of slices. Fetch and draw slice sagittal. Current sagittal index sagittal context. Function update coronal view increment. Coronal index equals current coronal index plus increment 100%. Adjust according to number of slices. Fetch and draw slice. Coronal, current coronal index, coronal context. Document.add event listener key down. function event. If event.code equal arrow up, update axial view 1. Else, if event.code equal arrow down, update axial view next 1. Else, if event.code equal arrow left, update sagittal view 1. Else, if event.code equal arrow right, update sagittal view next 1. Else, if event.code equal page up, update coronal view 1. Else, if event.code equal page down, update coronal view nice 1. Mouse navigation axial canvas.add event listener wheel function event. If event delta y 0, update axial view 1. Else, update axial view -1. Sagittal canvas.add event listener function event. If event delta y 0, update sagittal view 1. Else, update sagittal view -1. Coronal canvas.add event listener wheel function event. If event delta y 0, update coronal view 1. Else, update coronal view dice 1. Initialize views with the first slices fetch and draw slice, axial, current axial index, axial context. Fetch and draw slice, sagittal, current sagittal index, sagittal context. Fetch and draw slice, coronal, current coronal index, coronal context. Display a slice of volumetric data on the fourth canvas function. Fetch and draw volumetric slice. Let img new image, img.sarc/slice axial 0. You can choose an initial slice to display img.onload equals volumetric context.clearrect 0, volumetric context.canvas.width, volumetric context canvas.height, volumetric context.draw image img 0.
If it picks up on the problem, but it's working much better. Yeah, we need the controls, other mouse controls as well. Just send the image. Even no prompt. Let's see if it picks up on that fourth panel. And no errors at it, no. Where'd you get the errors from? It's always regenerating the whole. Show that the prop processing is going to generate all expected slices and they are correctly saved. Can you describe this image first before you're going making all sorts of assumptions? The fourth canvas is not blank. It is displaying essentially what the first canvas is displaying, but it doesn't look like the volumetric data. Correct endpoint, show correct canvas, targeting, data JavaScript. the JavaScript. Okay, did something to that fourth panel.
Thank you for clarifying that the fourth canvas is displaying the same content as the first canvas, axial slice, rather than the intended volumetric data. This means that the logic for displaying the volumetric data is not correctly implemented or being overridden by the current slice display logic. Steps to resolve the issue. 1. Correct the endpoint for volumetric data. Ensure the correct endpoint is called for the volumetric slice and differentiate it from the axial slice. 2. Ensure correct canvas targeting. Ensure the JavaScript function correctly targets the fourth canvas for displaying the volumetric data. Updated JavaScript. Ensure the JavaScript fetches and displays the correct volumetric data on the fourth canvas without duplicating the axial slice. Main JavaScript. Canvas setup for 2D views. Let axial canvas equals document.getElementById, axial view. Let sagittal canvas equals
Can you confirm the app by script? What I currently have is working better. Ensure that the correct slice of volumetric data generated and placed here. Well, they are not there. It's generating. This should not be. What on earth? Yeah, we need to fix the pre-processing. It's not generating the volumetric data. Why are you generating the whole code? Again, I don't understand. Can we fix the pre-processing Python code? It is not currently generating the volumetric data in the static folder. We need to fix that and correct the relevant bit in the JavaScript. Can you do this for us? By the way, if you want to make any jokes or something funny, not like ha 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 funny, but on topic funny, go for it. Yeah, this live stream today was a bit dry, wasn't it? We're still on 499 subscribers. Should we just continue streaming until we get to 500? Probably not. I mean, I can just, yeah, while it's generating, go check out binarykills.com. I can leave you with the live simulator for like 10 hours or something. Would that be fun? Life is still going. That's nice. We can add some rain. essentially the idea for it was you could potentially add a score where you have to keep a high life ratio and use as little water as possible, something like that. But yeah, go check out the website. Annoying scrolling
Sure.
through this thing.
Let's fix the pre-processing script to ensure that it correctly generates the volumetric data in the static folder. We'll also ensure the relevant bits in the JavaScript are updated accordingly. Just imagine the pre-processing script as a diligent chef, chopping up your MRI data into perfect little slices and then assembling a 3D model as the pièce de résistance for your brain viewing feast. Updated pre-processing script. Py. Python import nebable as neb, import numpy as np, import JSON, import os from skimage, import measure, import matplotlib.pyplot as plt. Def create slices nifty file output dar, img equals load nifty file, data equals img.getFdata. Create output directories if they don't exist. Make dir's output dar exist OK equals true. Axial dar equals os.path join output dar axial. Sagittal dar equals os.path join output dar sagittal. Coronal dar equals os.path join output dar coronal. Volumetric dir equals os.path join output dir volumetric. Add a directory for volumetric data. os.make dir's axial dar exist equals true. os.make dir's sagittal dar exist equals true. os.make dir's coronal dar exist equals true. os.make dir's volumetric dar exist equals true. Create the directory for volumetric data. Save slices for I in range data.shape, plt.imsave os.path.joindar, fipng, np.rot9d data I, cmap equals gray for I in range data.shiro, p.imsave os.path.sagittal.dar, fipng, np.rot9d, cmap equals gray. For I in range data.shape1, pl.imsave path join coronal da png, np.rot9i, cmap equals gray. Save a representative volumetric slice, e.g. middle slice, middle index equals data.shape2, 2plt.imsave path join volumetric dir volumetric.png np.rot90 middle index c gray. Def generate 3D model nifty file output file img equals n.meta file data equals img.getFdata data equals data np.max data normalize data for marching cubes. Extract surface using marching cubes verts faces normals values equals measure.marching cubes data level 0.5. Create model data equals metadata. Format version 3.1, type geometry, generated by JSON.3, vertices len verts, faces len faces, normals len normals, colors 0, UVS 0, 0, morph target 0, vertices, verts.tolist, faces, faces.tolist, normals, normals.tolist. Save model data as JSON with open output file W as f.json.dump model data f, if name equals nifty file equals to sub 0 ses1 t1w.ni.
Okay, this works with no errors. However, the volumetric data is just one static image. What's up with that? Just explain before generating any code. Jokes are okay.
Explanation of volumetric data as static image. The current implementation for the volumetric data simply takes a single 2D slice from the middle of the axial plane and displays it as a static image. This is why you're seeing just one static image instead of an interactive volumetric representation. What's happening? 1. Pre-processing script. The script selects a single slice, the middle slice, from the axial orientation and saves it as a PNG image in the volumetric directory. 2. JavaScript. The code fetches this single static image and displays it on the fourth canvas. Why a single slice? This approach was chosen for simplicity, creating a true interactive volumetric visualization where you can explore different slices in 3D requires more complex handling, such as loading and rendering multiple slices interactively or using specialized libraries for 3D volumetric rendering. Potential improvements. 1. Interactive slicing. Allow the user to interactively scroll through multiple slices in the volumetric view, similar to how axial, sagittal, and coronal slices are navigated. 2. 3D volumetric rendering. Implement more advanced techniques to render and explore volumetric data in 3D. This involves using libraries and techniques that support volumetric rendering, such as 3JS with volume rendering extensions or other specialized tools. The big picture. Think of it like this. You're currently showing a single frame from a 3D movie instead of letting users watch the entire movie. To let them explore the full 3D experience, you'll need to step up the complexity of your visualization approach. Next steps. 1. Interactive slicing. Update the pre-processing script to ensure all slices of the volumetric data are saved. Modify the JavaScript to allow users to scroll through these slices. 2. Advanced 3D rendering. Investigate and implement volumetric rendering techniques using suitable JavaScript libraries. Would you like to proceed with making the volumetric data interactive, or would you prefer to explore more advanced 3D volumetric rendering?
Yes, I would like the volumetric rendering to be proper. So volume structure that I can twist around, and I would also like to be able to zoom in and out. I want to be able to flick through the slices back and forth. We need some sort of indication of where we are inside the brain, the head. Before generating any code, how you gonna do this? Jokes are welcome.
How to implement proper volumetric rendering. All right, let's dive into the plan to create a proper volumetric rendering of your MRI data. We want to ensure you can twist, zoom, and flick through slices with some indication of the current position inside the brain. Steps and strategy. 1. Pre-processing. Generate the full set of 3D volumetric data and save it in a suitable format for rendering. Use 3JS for volumetric rendering in the browser. 2. Setup. Use 3JS to create a 3D scene. Load the volumetric data and create a 3D texture. Set up camera controls for rotating, zooming, and panning. 3. Slice navigation. Implement slice navigation to flick through the different slices. Display a 3D cross-section plane to show the current slice position. 4. UI elements. Add UI elements to indicate the current slice position. Provide controls for users to navigate through the slices. Plan in detail. 1. Pre-processing. We'll extend our pre-processing script to create a 3D texture from the MRI slices. This will involve saving the data in a format that Three.js can load, like a 3D texture or a series of 2D textures. 2. Three.js setup. We'll set up a Three.js scene with a perspective camera and controls. Orbit controls for rotating and panning. Zooming using mouse wheel interactions. Loading the volumetric data into a 3D texture. Nash 3. Slice navigation. Use the arrow keys and UI controls to navigate through the slices. Display a cross-sectional plane within the 3D scene to show the current slice position. 4. UI elements. Add indicators, e.g. a slider or numerical display for the current slice. Provide interactive controls for users to change slices. Jokes interlude. Imagine the volumetric rendering as playing a game of Operation, but instead of a buzzer and funny bone, you're navigating through the intricacies of the human brain in glorious 3D. Just make sure you don't touch the sides. Implementation strategy. Pre-processing. We'll modify the pre-processing script to generate a 3D texture. This involves storing each slice in sequence, which can then be loaded into Three.js. Three.js volumetric rendering. Three.js will handle rendering the volumetric data using a shader to display the 3D texture. We'll use orbit controls for interaction, allowing you to rotate and zoom the model. We'll add keyboard and UI controls to navigate through the slices. A cross-sectional plane in the 3D scene will highlight the current slice. Example code flow. No code yet. 1. Pre-processing. Load the
Do we update the current code that we have or generate the code from scratch? I like how the voice to text works. It's actually correcting the sentences somehow. Significantly update the current code. Just essentially need to make sure there are no templates. It's 72 lines of code. How's it much simpler, shorter? Because the pre-processing should be running without the Flask application, so we can run that first. It should update the folders for us. You generating code. Clear. Are you regenerating code even if no changes are made? It will really time me out soon, isn't it? I did notice yesterday it did time me out for GPT-4, but not for not. Not for not. Whatever 4.0.
D equals loader.load / data volumetric append.
Okay, we have JavaScript as well. 1 or 2. That's suspiciously longer. Application won't run. Actually need to run the Flask app. No errors, but yeah, also the panning is not great. And where is the what is the model? Where is the model? Where is the model? Just creating a zip file to load into the model. Can we test the code? We still don't see the volumetric data on the fourth panel. Okay, did I get a timeout? It doesn't look like it's still loading. It's 173 megabytes. The two largest, I mean. Must be. must be too large. F index app by a process, pre-process, sorry. Don't generate any new code yet. Just text with what the solution might be.
Analysis of the current state. From the provided files and the information you've shared, here's a summary and potential solution for why the volumetric data might not be displaying correctly. 1. Pre-processing script, preprocess.py. The script generates slices for axial, sagittal, and coronal views and also saves volumetric slices. However, the volumetric slices are simply the same axial slices saved under a different
Okay,
directory.
that's good to know.
2. Flask backend, app.py. Serves the slices correctly. There is no special handling for volumetric data beyond serving the slices. 3. Frontend, index.html, and modes the volumetric slice from /static/data volumetrics volumetric.png. This slice is just a single 2D image, not a full volumetric rendering. Chahak, why the volumetric data is not displaying correctly. The volumetric data displayed is currently just one static slice, not a true volumetric representation. This is because the pre-processing script only saves individual slices and the front end only loads a single 2D image. Solution overview. To display proper volumetric data, 1. Generate a 3D texture from the MRI data. 2. Load this 3D texture in Three.js and render it interactively. Implementation steps. Step 1. Update pre-processing script. Save the MRI data as a 3D texture that Three.js can use. This involves storing the data in a format suitable for WebGL. Step 2. Update Flask backend. Ensure it serves the 3D texture file. Step 3, update frontend 3JS. Load and render the 3D texture. Add controls for interaction, e.g. rotation, zooming, slicing. Pre-processing script update. You need to create a 3D texture from the MRI data. This can be saved in a format like a raw binary file, which 3JS can read. Updated preprocess.py. Python import nibable as nib, import numpy as np. Import os. Def create slices nifty file output dar. img equals nib.load nifty file. Data equals img.get fdata. Create output directories. If they don't exist, os.makedir's output dar exist equals true. Axial dar equals os.path join output dar axial. Sagittal dar equals path join output dar sagittal. Coronal dar path join output coronal. Volumetric dar equals os.path join output dar volumetric. os.makedir's axial dar exist equals true. os.makedir's sagittal dar exist ok equals true. os.makedir's coronal dar exist ok true. os.makedir's volumetric dar exist ok true. Save slices for I in range data.shape, plt.imsave os.join axial dar at png, np.rot90 data.i, cmap equals gray. For I in range data, plt.imsave path join sagittal dir fpng np.rot90 data I, cmap equals gray. For I in range, pl.imsave of path join coronal dar fpng np.rot data I, cmap gray. Save volumetric data as a raw binary file. Data.to file os.path volumetric dir volumetric.raw. If gore name nifty file equals sub 0 or sesquas-t1w.ni. Original nifty file output dir equals statics data. Directory to save slices create slices nifty file output dir. Flask backend update. Ensure the Flask backend serves the new 3D texture file. Update app.py to include the following. Python at app.route/volumetric, def serve volumetric. Volumetric path equals static data /volumetric/volumetric.raw. If os.path.exists volumetric path, return send file volumetric path. Return JSONify error, volumetric data not found, 404. Frontend update. Update the frontend to load the 3D texture and render it using 3JS. Update main.js. JavaScript, basic setup for 3D view. Let scene equals new3.scene. Let camera is new3 perspective camera 5 window inner width / window dot inner height 0.1 1000. Let renderer equals new3.webgl renderer. Renderer.set size window inner width 2, window inner height 2. Document.get element by ID, volumetric view to pen child, renderer.dom element. Let controls equal to 3.orbit controls camera, renderer.dom element. Load volumetric data. Let loader equals new3.file loader. Loader.set response type array buffer. Loader.load/volumetric function data. Let texture equal 3 data texture 3D. New intate array data 256 256. Assuming 256 256 by 256 volume texture.format equals 3.red format. Texture.type equals 3.unsigned byte type. Texture.minFilter 3.linear filter. Texture.mag filter equals 3.linear filter. Texture.unpack alignment equals 1. Let material equals new 3.mesh basic material, map texture. Let geometry equal new 3 box geometry, 111. Adjust the size accordingly. Let cube equals new 3.mesh geometry material. Scene.add cube, animate. Let ambient light equals new 3.ambient light, 04040. Scene.add ambient light. Let directional light equals new 3 directional light xfff1. Directional light.position set 111, normalize. Scene to add directional light, camera.position z equals 5. Function animate, request animation frame, animate, controls.update, renderer.render scene, camera. /canvas setup for 2D views unchanged. Let axial canvas equals document get element by add axial view. Let sagittal canvas equals document.get element by ID sagittal view. Let coronal canvas equals document.get element by ID coronal view. Let axial context equals actual canvas.get context 2D. Let sagittal context equals sagittal canvas.get context 2D. Let coronal context is coronal canvas.get context 2D. Let current axial index equals 0. Let current sagittal index equals 0. Let current coronal index equals 0. Function fetch and draw slice orientation index context. Let img equals new image. img.sarc equals / orientation / doll index. img.onload equals context clear rect 0. Context.canvas.width. Context.canvas.height. Context.draw image 0. Context.canvas.width. Context.canvas.height. img.onrer equals console.error. An error occurred while loading the image slice. img.streak. Function update axial view increment. Current axial index equals current axial index plus increment plus 100 cent 100. Adjust according to number of slices. Fetch and draw slice axial. Current axial index, axial context. Function update sagittal view increment. Current sagittal index equal current sagittal index increment 100 cent 100. Adjust according to number of slices, fetch and draw slice sagittal, current sagittal index, sagittal context. Function update coronal view increment. Current coronal index equals current coronal index plus increment plus 100% 100. Adjust according to number of slices, fetch and draw slice, coronal, current coronal index, coronal context. Document.add event listener, key down, function event. If event.code equal arrow up, update axial view 1. Else if event.code arrow down, update axial view -1. Else if event code arrow left, update sagittal view 1. Else if event code equals arrow right, update sagittal view -1. Else if event.code equals page up, update coronal view 1. Else if event.code equals page down, update coronal view. / mouse navigation axial.add event listener wheel function event. If event.delta y0, update axial view 1. Else update axial view -1. Sagittal canvas.add event listener wheel function event. If event.delta y0, update sagittal view 1. Else update sagittal view context. Fetch and draw slice sagittal, current sagittal index, sagittal context. The error you're encountering, WebGL, invalid operation, bind texture, textures cannot be used with multiple targets, indicates that there might be an issue with how the texture is being loaded or used in the Three.js scene. To resolve this, we'll need to ensure the 3D texture is correctly formatted and utilized in a way that WebGL can handle. Instead of using a data texture 3D, which might be causing the issue, we can load the volumetric data into a Three.js texture array or a series of textures. Approach: using a texture array. We'll convert the volumetric data into a texture array, which Three.js can handle better. Let's update the preprocess.py script to save each slice as a separate image, and then load these images in Three.js. Update preprocessing script. Updated preprocess.py, Python import nibable as nib, import numpy as np, import os, import matplotlib.pyplot as plt, def create slices nifty file output dar, img nib.load nifty file, data equals img.get fdata. Create output directories if they don't exist, os.makeDar's output dar exist okay true. Axial dar equals ospath.join output dar axial. Sagittal dar equals path join output dar sagittal. Coronal dar equals path join output dar coronal. Volumetric dar equals path join output dar volumetric. os.makeDars axial dar exist okay equals true. os.makeDars sagittal dar exist okay true. os.makeDars coronal dar exist true. os.makeDars volumetric dar exist ok true. Save slices for I in range data.shape, plt.imsave, ospath.join axial dir, fpng, np.rot90, cmap equals gray. For I in range data.shape, plt.imsave, os.pathjoin sagittal png, np.rot90 ip, cmap equals gray. For I in range data.shape, pathjoin coronal dir fva, png ent.rot90 I gray. Save volumetric data as a series of slices for I in range data.shape,
I'll just have to finish this next time. Let me know if you have done something similar. It's working better for you or not. Am I using the correct libraries or not? And do let me know, and I'll see you next time.